So we're gonna go through notes. And then your assignment, I guess, is, yeah, it's right under the homework, right? You just have to do it tonight at home. Now, I will tell you, I am not going to talk about every single little bitty detail in this section because we've done section 11.2 before, but we've done it in 2 dimensions. Now we're gonna do it in 3 dimensions, okay? So things like adding vectors together, I'm not gonna go through that again. The stuff with unit vectors, I'm not gonna go through that again. I need you to go back to your memories from right before Christmas, okay? Now, you are the one pre-calculus class that we didn't get to go through 3-dimensional coordinates with. Don't worry, I think you're gonna be fine. Okay, so you're gonna take 2 full-length practice tests, and the best one, I'll put in the grade book as your score, okay? So if you do like super awesome on the first exam and you miss 2 days of the second exam, you don't have to make them up if you don't want to, okay? I find that at the end of the year, there's a lot of absences, especially in 6th hour, right? For soccer games or track meets or AP tests, whatever. Okay, so like last year we took 1 test and then you got to retake 2 of the 4 parts. Okay, we have time to take 2 full-length tests. Okay, so number 1, those of you taking AP test, man, you're gonna be ready. Number 2, if you have some absences, then it's easier to work around those and you don't feel like you have to get a part made if you're happy with it. Okay. I think you listen to half of that, but does that make sense? No, like, so pretty much if you're not here that day, you wouldn't have to make it up. I can't stop you. Okay. All right, so 3 space is divided up into 8 octants. So in 2 space, we have 4 quadrants. In 3 space, we have 8 octants. Okay, so the x-axis is coming out of the paper at you. The y-axis is running this way, and the z-axis up. Okay, so if you notice, look at my little right there. We have 1, 2, 3, 4, 5, 6, 7, 8 sections of this 3 space. These are our octants. 1, 2, 3, 4, 5, 6, 7. So what happens when we plot 3-dimensional coordinates? We move in the XY plane first, and we make like our parallelogram, like X, Y. Here's our XY coordinate. And then we lift it up or down for our Z coordinate. What's the problem? Well, the XY plane is like the floor. Okay, so we've taken it from on the paper. It's still, I mean, it's still a plane, right? And the z-axis is coming out. Okay, so to calculate the distance in 3 dimensions, guess what? Really not that much different than how you calculate distance in 2 dimensions. We just have a third piece underneath. Everything's still square. But you can write R. So you're going to be given two coordinates under the square root. You're going to take x minus x squared plus y minus y squared plus z minus c squared. It's just that third dimension added in. Okay. Now, in 3 dimensions, you would have a sphere instead of a circle. So notice how the equation of our sphere, x minus x squared, y minus y squared, z minus z squared equals r squared, where this x naught, y naught, z naught is our center. What? No, it's like there's still piles of snow right here. I didn't know there. I actually remember you doing that. Yeah. Didn't you get in trouble though for shoveling the track?
No, you can shovel. They try to get us in trouble with their buildings.
Yeah.
So it doesn't matter.
Okay.
But then they literally, we shoveled it and then they came by the machine the next day. So we didn't need to shovel it, which matches.
Okay, and then one more topic, midpoints. The average of the x's, the averages of the y's, the average of the z's. Okay, you know how to find a midpoint. It may have been a couple years since you've had to find a midpoint, but just remember we're taking the average of each of the coordinates for our midpoint. So I've talked about distance, I've talked about midpoint, and I've talked about the equation of a sphere. Do you think that these need to be added? Do you think that I have a problem that can incorporate all 3?
Quadratic formula.
Quadratic formula.
You were.
Theory. There we go. Joke about it correctly. Ugh. Okay, so we have a diameter that has endpoints at 5, 2, 1 and 1, negative 4, 5. And what? Just for you. And we want to write the equation of the sphere. So what 2 things do we need to know about our sphere in order to write the equation? Center and radius. I have neither one of those things. How? How do we calculate the center? I have the end points of the diameter. Oh, the midpoint. Jane, what's our midpoint? Okay. Now we need the radius. We have 2 different ways we can find the radius. What would distance from? Okay, so we can find the distance from end point to end point, and that would be considered our diameter. Or we can find the distance from center to end point, and that would be our radius. Which one would you like to do? Okay. So our radius is going to be the square root. Which point would you like to use? This one sounds good. I like the one with all positives. Okay, so we have 5 minus 3, the quantity squared. 2 minus -1, the quantity squared. And 1 minus 3, the quantity squared. What's that number under the radical? 17? Square root of 17? Don't just say yes because one person said it, like I want.
Yeah, I concur.
So our equation would be. What? Do you not agree? So since our radius is the square root of 17, radius squared is going to be 17. So I have that written down. I will also tell you that you're probably going to encounter a problem where you have like x squared plus 5x plus y squared minus 6y plus z squared plus 10z. And you're going to have to complete the square 3 times in order to get the equation of your sphere. Okay, but I have complete faith in you. You're going to be fine. Okay, so let's talk about vectors in 3 space. And that's really what the most important thing about this week is going to be. Okay, we're going to talk about vectors, like just some reminders today. Tomorrow we'll talk about the dot product, and then Thursday we'll talk about something called the cross product. Okay, so remember how we had I and J? Now we have I, J, and K. Okay, so we have a couple different ways that we can express vectors. We either have the component form, where we have the chevrons, or we have the linear combination form. Now that we're in 3 dimensions, you are going to see the linear combination form a lot more than you're going to see the component form. I just want to warn you. Okay, and then since we have to find the length, the magnitude of a vector, we're going to apply basically the distance formula in 3 space to find the magnitude. So that's what that is right there. Like, I'm probably not going to go through an example of finding the well, do you want to find the magnitude of this vector? Would that help you? Okay, let's go to this guy right here. 2, -1, 5. If we wanted to find the magnitude of vector v, we would just take the square root of 2 squared plus -1 squared plus 5 squared. So what do we got? Square root of 30. If I wanted to make a unit vector in the same direction as that guy, first of all, what's a unit vector mean? Bless you. Magnitude 1. So we can take the magnitude of v and divide it through our vector. So now we have created a Vector with magnitude 1 that goes in the same direction as vector v. Let's remember, how do we tell if two vectors are going in the same or opposite directions? Okay, I need a little bit more. The numbers matter also. Like the vector 2, -1, 5 is parallel to the vector 2 divided by radical 30, -1 divided by radical 35 divided by radical 30, which is also parallel to the vector -10, 5, -25. They are all blank of each other. These are equal. What? Oh, they're like scalar multiples of each other. Like you can multiply by a number and get this one. Do you see what I'm saying? Do you see what she's saying? Okay. So if vectors are scalar multiples of each other, we know that they are parallel. Okay. Two vectors are parallel if you can multiply one by a scalar to get the other. So here is vector u, here is vector v. Since we can take -2 times vector v and get u, these two vectors are parallel. So we have only one more example. Okay. Danny, let me know when you're ready. You guys get to start your homework. Okay. So we are going to actually we're going to use this concept of parallel vectors to show if 3 points are collinear. Okay, so if you have 3 points and you create 2 vectors out of the 3 points, if those vectors are parallel, then your points should make a line. Now, why am I not like finding the slope? We're in 3 dimensions. Do you know how to do 3-dimensional slope? Nope. Nope. That's why we have vectors. Okay. So if I have 3 points that are not collinear, then when we create the 2 vectors, they're not going to be parallel. Okay. But if our 3 points are in a line, then our vectors, whether they're going the same or opposite directions, are going to be parallel. So let's create 2 vectors out of these 3 points. How about vector PQ? Remember, when we create a vector, we need to take terminal minus initial. So if we take terminal minus initial, we would get 1, 3, -3. Do you agree with that? Okay. Would you like to create PR, QR, RQ? Which one you want to create now? What?
QR.
And if we create QR, 4 minus 2, 7 minus 1, and -6 minus 0. What's true about PQ and QR? They're parallel. Notice how we can multiply PQ by 2 and we get QR, okay? So, trying to think of how I want to word this here. P, Q, and R are collinear. Since PQ is parallel to QR and share 1 point. If your two vectors were not parallel, then you would not have collinear. Okay. So in Google Classroom, I have already uploaded chapter 1 book. By chapter 1 and chapter 1. So you can go ahead and get started on your chapter 11.2 homework since we don't have our work day tomorrow. But I don't think any of us are gonna complain about our snow day, right? Yes. Aren't you glad you stayed?
Yes.